Hi, this is Nuclear Physics Lesson 2. This one's Properties of Nuclear Radiation. Again, a bit of a recap from GCSE mainly. So, radioactivity. The atoms of some substances are unstable and they give out radiation from their nuclei all the time. Whatever is done to them, these substances are said to be radioactive. So the first three types of radiation discovered were alpha particles, beta particles, and gamma rays. By this pair, Henri Becquerel and Marie Curie. And I believe Marie Curie's husband was involved as well with the research on radioactivity. So when it says that the substances are radioactive all the time, you can't do anything to a radioactive substance to make it not radioactive. You can't change the temperature, you can't change the pressure, you can't put it in a different location. It will always be radioactive. Alpha, beta, and gamma radiation. So alpha is simply a helium nucleus, so 2 protons and 2 neutrons. Beta particles, a high-speed electron. Beta decay from year 12. It's come from the nucleus where a neutron has decayed into an electron and a proton, and the electron is fired from the nucleus. Typical speeds might be, approximately 10% the speed of light, but they do have a range of kinetic energies, which we'll discuss later. Gamma rays, they are simply very high-frequency electromagnetic waves, so higher energy than X-rays. So, yeah, very high frequency indeed. Remember to pause at any time if you want to make any notes. And gamma rays are produced when there's an unstable nucleus that loses energy. Gamma rays are typically given off after, most likely after an alpha decay or a beta decay. So what about the penetrating power of alpha, beta, and gamma? So paper or a few centimeters of air is enough to stop alpha particles. Then you might need a meter of air, or up to a centimeter of aluminium. A few millimeters though will also work to stop beta particles. And several centimeters of lead or up to a meter of concrete will be required to stop gamma rays. Remember to pause to take any notes. So what about deflection by magnetic fields? It's pretty straightforward. The alpha and the beta will be deflected because they have charge. The gamma rays will just pass through undeviated. So alpha and beta particles are deflected in opposite directions due to their opposite charges. And due to their much larger mass, the alpha particles are deflected far less than beta. Remember, alpha particles are approximately 8,000 times more massive when compared to a beta particle. And again, gamma rays are not deflected because they are not charged. So let's move on. So what about deflection by electric fields? So the alpha, as it's positively charged, 2 protons and 2 neutrons, will be deflected towards a negative side of an electric field. And beta, being a fast-moving electron of negative charge, will obviously move towards the positive side of an electric field. So alpha and beta particles are deflected in the opposite directions due to their opposite charges. And due to their much larger mass, alpha particles are deflected far less than beta particles. And gamma rays, once again, are not deflected because they're not charged. So a bit more information. Alpha particles are the same energy for any given source. They have a specific alpha particle energy as shown in the graph in the upper left-hand corner, where there's some examples: polonium, plutonium, americium. And beta, they get a range of energies. And that's simply because the kinetic energy is shared with the neutrino and the daughter nucleus. And gamma is the same as alpha, same energy for a given source. This answer can come up as an examination question. So the question might simply ask, why do betas have a range of kinetic energies? So just a bit more information. Nothing really difficult on this video. So the nature of alpha particles, just going to go for this information one little piece at a time. So alpha particles are simply 2 protons and 2 neutrons of the helium nucleus. The beta particles, high-speed electron, and gamma is a photon in the mega electron volt range. It's a very high frequency electromagnetic wave. Absorption, paper or thin foil for alpha. Beta, up to 5 millimeters of aluminium. And several centimeters of lead or 1 meter of concrete is sufficient to vastly reduce gamma radiation. Range in air of alpha up to 10 centimeters. So not very far. So alpha is not particularly dangerous at distances greater than 10 centimeters. Obviously, alpha will be exceptionally dangerous if you ingested it. Alpha inside the human body wouldn't be able to escape. It would lead to, cancers, destruction of DNA, and other nasties. It probably result in death. So alpha inside the human body, not a good idea. Beta radiation up to 1 meter. So again, just outside the human body, beta radiation would be very dangerous, especially when we'll move on to ionization shortly, and then we'll discuss that. And gamma follows an inverse square law. So the range in air is very long, hundreds of miles potentially. So in terms of ionization, alpha particles are the most highly ionizing, 10 to the 4 ions per millimeter. Beta radiation, moderately ionizing, 10 to the power 2 ions per millimeter. The ionization power of gamma when compared to alpha and beta is very weak. So let's talk about the dangers. So we talked about alpha, very highly ionizing, very dangerous at short range. Beta radiation up to 1 meter away from the body or in close proximity is very dangerous, as the beta radiation can pass inside the body, causing damage. And again, they're still moderately ionizing, 10 to the power 2 ions per millimeter. So beta just outside of the human body is very, very dangerous. You should, if you have a beta source, you should keep your distance. Definitely don't point it at yourself or anyone else. And gamma's ionization is very weak. However, the range is very long, and in a normal scenario, there's nothing to absorb it. So gamma radiation will pass through the human body quite easily, but fortunately isn't too ionizing. So hopefully doesn't cause too much damage unless there is a lot of gamma radiation. So deflected by a magnetic field, alpha, yes. The beta is a yes as well, but it's the opposite direction to alpha particles. And they're more strongly deflected due to their low mass, or lower mass compared to alpha. Gamma is not deflected by a magnetic field. And the same stands for electric fields as well. Which we discussed earlier. Exactly the same as the magnetic fields. The deflection for the electric field for the alpha is towards the negative. So I'll just put to the negative. And this one is to the positive. How about the energy of each particle or photon? Alpha, remember, is constant for a given source. Beta will give a range of kinetic energies, and the explanation was given earlier. Gamma is also constant for a given source. So quite a lot of information to learn. Hopefully you've got some concise notes that you can use. And try to remember all this information and to learn it. Alright, thanks for watching. The difficulty will increase drastically on the next video, which I'm sure you're looking forward to. But thanks for watching, and I'll speak to you then. Thank you.